So, uh, what does it fundamentally mean to have a Bitcoin? Really?
It's a great question. And you hear all these answers, right? Digital gold, mining.
Yeah.
These analogies, they kind of obscure what's actually happening.
Yeah, they don't really tell you the how.
Exactly. So the mission for this deep dive is, well, let's cut through that. Let's try to give a direct, sort of step-by-step picture of the technology itself, what the math, the cryptography is actually doing.
Right, because you might think, look, I just want to buy some, maybe use it. Why dig into the weeds?
And that's fair. You don't need to be, a cryptography expert to
Yeah.
use it. Just like driving a car doesn't require knowing combustion engine physics.
True.
But this is different. The whole foundation, it's built without a central bank, without any single trusted authority. It relies on this decentralized, trustless verification.
Trustless verification, okay.
Yeah, and with all the hype, the investment, understanding that core idea, it's not just interesting, it's pretty healthy, I think. Helps you navigate it all.
Okay, so where do we start unpacking that? Maybe not with Bitcoin itself.
Good idea. Let's put crypto aside for just a moment. Imagine a really simple scenario. You and some friends, you lend each other small amounts of money all the time.
Yeah, like splitting dinner bills, spotting someone $20, constantly swapping cash gets annoying.
Right. So you decide, let's just keep a shared list,
Yeah.
like a Google Sheet or something. Anyone can add a line. Alice pays Bob $20. Bob owes Charlie $40. A communal ledger.
Okay, simple enough. Everyone adds their IOUs, and then what? At the end of the month, you tally it up and settle the balances with real cash.
That's the basic idea. But there's an immediate problem, isn't there?
Sure.
Trust. If anyone can write on this shared sheet, what stops Bob from just adding a line saying Alice pays Bob $100, even if Alice never agreed?
Ah, right. Bob could just make stuff up. We need proof.
Exactly. Proof that the sender actually authorized it. And that brings us to our first bit of crypto magic.
Digital signatures.
Okay, digital signatures.
Alice needs a way to attach something to that transaction that only she could have created. This uses two keys, mathematically linked. A public key, which everyone can see.
Right. And a private key or a secret key. That one she guards fiercely. It's hers alone.
So how do they work together?
The private key is what creates the signature. Think of it like a unique stamp. The public key is what verifies the signature. Anyone can use the public key to check that, yes, the signature was definitely made by the corresponding private key.
So like a wax seal, everyone recognizes the imprint, but only Alice has the actual seal press.
That's a decent analogy, and the security here is just immense. It's mathematical.
How immense?
Well, the signature isn't static. It depends on the exact message and the private key. Change one tiny detail in the message, you need a completely different signature.
Okay.
And we're talking about, say, 256-bit security. That means the number of possible keys or signatures is 2 raised to the power of 256.
Which is big.
Astronomically big. Like, estimates are, it's roughly the number of atoms in the known universe squared.
Yeah.
Trying to guess the private key or fake a signature for a message, it's infeasible. Just guessing randomly is your only shot.
Wow. Okay, so forgery is out. But what if Bob just copies a valid line? Alice pays him $100, it's signed correctly. Can't Bob just copy and paste that line 5 times onto the ledger?
A good point. The replay attack.
Right.
Simple fix, thankfully. Every transaction message has to include something unique. A transaction ID, a sequence number, something. So if Alice really wants to pay Bob $100 5 times...
Each payment needs its own unique ID and its own signature.
Exactly. Copying doesn't work. Problem solved.
Okay, so digital signatures handle the authorization part. We know Alice said to pay Bob, but we still have that problem from before, right? The ledger just tracks who owes what. We're still relying on everyone to actually pay up in real dollars at the end of the month. What about Charlie, who ran up a huge debt on the sheet and then just vanishes?
The honor system flaw. Precisely. The ledger tracks IOUs, not real, settled value.
So how did Bitcoin solve that?
This was a really clever leap. Get rid of the need to settle in outside currency, like US dollars, altogether.
How do you enforce value just on the ledger itself?
You start by giving everyone an initial balance. Maybe everyone puts $100 into a conceptual pot at the very beginning. That's recorded on the ledger.
Okay, everyone starts with $100 on the ledger.
Right, and then you enforce one crucial rule. The system itself, the protocol, will reject any transaction where someone tries to spend more than their current balance, according to the ledger history.
So you can't write a check, you can't cash, based on the ledger's own records.
Exactly. And this is the pivot point. To even know if Alice can send Bob $100, you have to look back through the entire history of transactions involving Alice.
You need the full history to validate any new transaction.
Yes. And suddenly, we're not just tracking IOUs for dollars anymore. We're trading, well, let's call them ledger dollars, LD. The value is internal to the system.
So the history of all the valid transactions is the money.
You got it. That history is the currency.
Okay, that's a big concept. And if the currency is just the ledger history, we don't need that central Google sheet anymore, right? We can decentralize. Everyone keeps their own copy.
Perfect for decentralization. But it creates the next massive problem. Consensus.
Consensus, meaning everyone agreeing.
Yeah. If everyone has their own copy, how do we make sure everyone has the same copy and agrees on the order of transactions? Imagine Alice has 100 ledger dollars.
Okay.
She broadcasts a transaction, pay 100 LD to Bob. Then, like a split second later, she broadcasts another one, pay 100 LD to Charlie.
Uh-oh. She only has 100 LD. She's trying to spend the same money twice.
Exactly. The double spend problem. Some people on the network might see the Bob transaction first. Others might see Charlie's first, whose ledger copy is correct.
Yeah.
How does the network agree on one single history? Without that agreement, the currency collapses.
Right. That seems like a showstopper. How do you solve that without a central authority deciding?
This is the core genius of Bitcoin, what Satoshi Nakamoto figured out. The high-level idea is, well, it sounds almost too simple. The network agrees to trust whichever version of the ledger has had the most computational work poured into maintaining it.
Computational work? Like computers working hard. How do you measure that?
Through another cryptographic tool, hash functions. Specifically, Bitcoin uses SHA-256.
SHA-256. Okay. What's a hash function do?
Think of it like a mathematical fingerprint generator. You can feed anything into a text, data, a list of transactions, and it spits out a fixed size string of characters, the hash.
A fingerprint for data.
Kind of.
Mm-hmm.
And it has critical properties. One, the output looks totally random. Two, change just one tiny bit of the input.
And the output hash changes completely?
Completely, unrecognizably.
Yeah.
And three, crucially, it's a one-way street. You cannot figure out the original input just by looking at the output hash.
Yeah.
The only way is guessing inputs and checking the hash. Brute force.
Okay, one way, sensitive to changes, looks random. How does that measure work?
This leads to proof of work POW. Imagine someone, let's call him a miner, gathers a bunch of recent transactions.
Right.
They bundle these transactions into a block. Now, the work is to find a special number called a nonce.
A nonce.
Yeah, just a number. They have to find a nonce such that when they add it to their block of transactions and run the whole thing through the SHA-256 hash function, the resulting hash starts with its specific, very unlikely pattern, like, say, 30 leading zeros.
30 zeros? Why? Is that hard to find?
Incredibly hard. The chance of a random hash starting with that many zeros might be, say, 1 in a billion, or even less, depending on the network's current difficulty.
So they just have to keep trying different nonces, hashing the block over and over until they get lucky.
Exactly. It requires immense computational power trying billions or trillions of nonces per second. That's the work. But checking if they found it, that's super easy. Anyone can take the block, the claimed nonce, run the hash function once, and see if it starts with the required zeros.
Hard to find, easy to verify. That's the proof.
That's the proof of work. The block contains the transactions plus this nonce that proves the work was done.
Okay, so miners do work to create blocks of transactions. How does that create the agreed-upon ledger?
Here's the final key piece. Each new block in its header data must include the hash of the block that came immediately before it.
The hash of the previous block? So they're linked together.
Precisely. Block 101 contains the hash of block 100. Block 102 contains the hash of block 101. It forms a chain, a blockchain.
Okay, I see the chain metaphor now.
And think about the security implications. If someone tries to tamper with an old transaction, say back in block 100.
That changes the data in block 100, which changes its hash.
Right, and since block 101 contains the old hash of block 100, block 101 is now invalid, and so is 102 and 103. The whole chain breaks from that point forward.
So to cheat, you'd have to redo the proof of work for block 100 and every single block after it, and do it faster than the rest of the network is adding new blocks.
Exactly. You'd have to essentially overpower the entire honest network's computational effort to make your fraudulent chain the longest, the one with the most proof of work.
Wow. Okay, that sounds incredibly difficult.
It's designed to be. So mining is this process. Miners listen for new transactions, bundle them into a block, and then race, burning electricity, to find that winning nonce.
It's like a giant continuous lottery where the ticket price is computation.
That's a good way to put it. The first one, to find the nonce, gets to broadcast their valid block to everyone else. Others verify it quickly and add it to their copy of the chain.
But why would anyone do all that work? It sounds expensive.
The incentive? The block reward. The miner who successfully finds the nonce and gets their block accepted onto the chain is allowed to include a special transaction at the very top of their block.
What kind of transaction?
A transaction that creates new Bitcoin out of thin air and pays it to themselves.
Ah, so that's where new Bitcoins come from.
Yep. It started at 50 BTC per block back in 2009. But the protocol dictates that this reward gets cut in half roughly every 4 years, every 210,000 blocks.
The halving, I've heard of that.
Right. So it went from 50 to 25, then 12.5, now 6.25 BTC per block. This ensures there's a predictable decreasing supply, capping out at a maximum of 21 million BTC ever.
And eventually, the block reward will be tiny. What happens then?
Miners will primarily rely on the transaction fees that users include with their payments to incentivize miners to pick their transaction for inclusion in a block.
Okay, so now we can finally tie it back to trust. How do I trust a transaction I receive?
In this decentralized world, you trust by consensus, specifically the consensus shown by the chain with the most accumulated proof of work, the longest chain.
Because that represents the majority of the network's effort.
Exactly. To trick you with a double spend, an attacker would need to create a competing chain containing the fraudulent transaction and then make that chain grow faster than the honest chain.
The 51% attack idea. They'd need more computing power than almost everyone else combined.
Right. They'd need to consistently outmine the rest of the network. It's possible in theory, but incredibly expensive and difficult to sustain for a large network like Bitcoin.
So, for practical purposes, if I receive a payment,
You should wait a bit. Don't consider it fully confirmed the instant it appears. Wait for a few more blocks, maybe 6, which is about an hour to be added on top of the block containing your transaction.
each new block makes rewriting that history exponentially harder.
Precisely. It becomes deeply buried under subsequent proofs of work.
Okay, the security model sounds robust, mathematically speaking, but let's play devil's advocate here. The contrarian view. Is it actually practical?
That's where the criticism comes in, especially regarding capacity. Remember, a new block is found only about every 10 minutes.
Right, that's built into the difficulty adjustment.
And each block has a size limit. It can only hold so many transactions, roughly around 2,400, give or take.
2,400 transactions every 10 minutes. That doesn't
no.
sound like very many on a global scale.
It's not. Compare that to something like Visa. They process, something like 1,700 transactions per second on average, and they can handle way more.
Yeah, that's a massive difference in throughput.
It's a direct consequence of Bitcoin's design choices, prioritizing decentralization and security over raw speed. This bottleneck is why transaction fees can get high.
Because miners have limited space, so they'll pick the transactions that pay them the highest fees first.
Exactly. It becomes a bidding war for block space when the network is busy. It's a trade-off. Security and decentralization versus speed and low fees.
Makes sense. It's not magic, it's engineering with trade-off.
Absolutely.
Yeah.
So let's try to wrap this up. What does it mean to have a Bitcoin, fundamentally?
Okay, my turn to try. It means you hold the private key that lets you create a valid signed transaction on this global shared ledger, the blockchain.
Yep.
And that ledger isn't secured by trusting a bank, but by the difficulty of faking the math, the hashing, and the sheer amount of computational work, the proof of work, that locks in the history.
Excellent summary. You don't need to do the math, but understanding that structure is key, especially with everything going on in the crypto world.
Right. Okay, one final thought then, something to chew on. We mentioned Bitcoin adjusts its difficulty, so blocks average 10 minutes apart, no matter how much computing power joins.
Right. A core feature.
So what about all these newer cryptocurrencies? Many claim much faster block times, maybe minutes or even seconds. How do they manage that balance? What trade-offs are they making between speed, security, and the amount of work needed to keep their chains safe?
That's a very good question to ponder. How do they tweak that equation?
Something for you, the listener, to maybe dig into next time.
Definitely.
All right, well, if you enjoyed this deep dive into how the blockchain actually clicks and whirs underneath, please do follow, like, and share it. It helps others find it.
Yeah, absolutely.
And if you want more insights like this, you can follow What Bitcoin Taught Me on all the socials: Twitter, X, Nostr, Bluesky, Threads, Instagram, Facebook, and LinkedIn.